Yeah, okay. Let's get started. Yeah. So today we're very happy to have Jiun-Haw Chu to give a talk on the debate, adding his evidence on the debate of electronic and nematic phase in the 135 family of vanadium kagome lattice superconductors. Yeah, Jiun-Haw has done many wonderful work in the case of electronic nematic phase in the case of iron-based superconductors. So he has extended his technique to other materials as well. So today we'll hear his view of what is happening in terms of electronic nematic phase in vanadium 135. Yeah, thank you, Jiun-Haw. Yeah.
Thank you, Pengcheng. Yeah, thank you for the invitation. And yeah, and it's really great to discuss these issues in this platform. So right, so today, as Pengcheng mentioned, I'm going to address this question. So is there a nematic transition in cesium vanadium-3 antimony-5? And the quick takeaway message is that there is no nematic transitions in this compound. And what we found is that in the elastoresistivity measurements, which is the canonical measurements to probe the nematic susceptibility in a solid, what we found is that there is a very weak and then temperature independent response in the nematic, the E2G channel. In contrast, there's a very strong A1G response, reaching up to a value of 90 or hundreds. No, this is a value that's comparable to the nematic susceptibility in iron-based superconductor, and then with a peak temperature around 20 Kelvin. So the most of the results in this talk is summarized in this recent preprint. Okay, so let me first acknowledge the people who actually done this work. So this work is primarily driven by my postdoc, Zhaoyu Liu. So he has done some very careful experiments, and then he has really shown the strong persistence to really go through this and then clarify the results. We also have some local collaborators, for example, from Jihui Yang's group and Xiaodong Xu's group at UW. And then this work really won't be happening if Pengcheng didn't really, send us the crystals and ask us to do some measurements. So we have really owe Pengcheng a thank you for this work. And some of the crystals are coming from Beijing Institute of Technology from China. And then we also have done some high field characterization on these crystals with the help of David Graf. And this work won't be, we won't be able to do this work without the support of these funding agencies. Okay, so I will start with a background of this vanadium-3 antimony-5 compounds. I will talk about the breaking of chimerisal symmetry and then the breaking of rotational symmetry. But because we have so many good talks on this topic in this online seminar series, so I will really just focusing on some experimental evidence associated with the symmetry breaking, especially the rotational symmetry breaking, and then discuss its relevant to nematicity. So after that, I will have an overview of the idea of electronic nematicity and then using iron-based superconductor as examples. And I'll argue that if there's really a nematicity in the cesium vanadium-3 antimony-5, this would be the case of a three-state pulse nematicity, and then which is fundamentally different from the IC nematicity in iron-based superconductor. And then it will be very exciting. But after that, I'm going to tell you that unfortunately this is not going to happen because from our elastoresistivity and elastocaloric measurements, we really see no evidence of nematicity in this compound. Okay, so let's start with the first the background of these materials. So this compound, cesium vanadium-3 antimony-5 or potassium or rubidium, the main platform for electronics activity is this vanadium layer, which form in a kagome lattice. So as all of you know, that this kagome lattice will support the electron structure with a lot of interesting features. For example, a flat bands, and also a Van Hook singularities and a Dirac points. So both the flat bands and Van Hook singularities will give you a very high density of states. And in particular for this compound, vanadium 3 antimony 5, the Fermi level is located very close to the Van Hook singularity, which there's already long before the discovery of this compound, there's a lot of theoretical studies suggesting that there's going to be a lot of interesting electronic phases arising from this Van Hook singularity. And then indeed, in all these three compounds, people have discovered that there is a high temperature, around 100 Kelvin, there is a phase transitions, which can be seen from this kink in the resistivity and then the heat capacity anomalies. And there's also a low temperature superconducting transition, which is around 1 or 2 Kelvin. So this is really driven by the Stephen Wilson's group that discovering these material systems and then characterizing the samples. So this high temperature phase transition is a charge density weight transition, which corresponding to a 2x2 modulations within the kagome plane, and then resulting in this trihexagonal or Star of David distortion. And this distortion has different kind of stacking, depends on the choice of the alkaline earth between the layers. So as we heard from last week talks, the real electron structure of these compounds is not as simple as this single orbits nearest neighbor tie binding model. There's much more complication. And the same is true for the case of symmetry breaking and phase transition. So here I'm showing you a figure from a very nice review put together by Stephen Wilson and Brendan Ortiz, which has just appeared on the archive. So in this figure, you can see this a very complicated landscape of phase transitions, where at the end of the right-hand side is the CW transition temperature, and then on the left, at the lowest temperature, you have superconducting transition. But in between, you see a series of temperature scale crossover, possible phase transition probed by different kind of experimental probes, especially for the cesium vanadium 3 antimony 5. So so I'm not going to go over all this transition and crossover. I'll just focusing on the evidence of phase transitions. So first is the time reversal symmetry breaking, evidence for time reversal symmetry breaking. So I think the first thing that got people's attention is this anomalous Hall effect that is detected just below charge density wave, which is very unusual because charge density wave typically is not a magnetic transition, so you don't expect an anomalous Hall effect. Nevertheless, it has been observed that there's this very strong nonlinear response in rho xy, which strictly speaking is not an anomalous Hall effect because in zero field, there's no spontaneous rho xy, but it does look like a Hall response of a soft ferromagnets, extremely soft ferromagnets that you don't even see a hysteresis to. So the saturation behavior, this is really reminiscent of a saturation of magnetization of the anomalous Hall in a soft ferromagnet. And then you might argue that the nonlinear Hall is not that unusual. You'll see two-band nonlinear Hall. You'll see nonlinear Hall in a two-band system with the electron and Hall carriers that will give you two different kind of slopes at high field and low field. But notice that in this very low temperature measurements, you already see some nonlinearity in a much higher field scale, which is superimposed on this low field nonlinearity. So to generate this kind of nonlinearity, you need at least 4 bands with very different mobility in order to generate this kind of nonlinearity. So, which is not totally impossible, but this also makes the anomalous Hall effect more convincing compared to the nonlinear Hall coming from two bands model. Okay, so this is the anomalous Hall. But in addition to anomalous Hall, there's also other probe that is detecting the time reversal symmetry breaking. For example, here I'm showing you the the mu-SR measurements, which I forgot to put on the reference, but this is a work by the PSI group, which they discovered that the muon relaxation rate changes near the CW transition, and it has a very dramatic field response, which make it very likely to be a electronics driven phase transition. So this time reversal symmetry breaking supports the idea of a loop current order, or you can think of it as a imaginary order parameter of the charge density wave. There's also other measurements like the optical Curry effect, which I will discuss a little bit when I talk about optical birefringence. So this is time reversal symmetry breaking. And there's even more evidence on the rotational symmetry breaking in this system. So first of all, there's a STM, I think actually the very first measurements, I think, is this C-axis resistivity measurements done by the Haihu Wen groups in Nanjing University, where they measure the resistivity along the C-axis, so transport current along the C directions, and then measuring voltage difference along the C direction, and then rotating the magnetic field within the AB plane, which they see a twofold pattern. And in addition to that, the SDM, for example, this is the work by Ilya Zelkovich group in Boston College, which they found that the intensity of the CW modulation for different Q is different. And then they see domains where this, when you go from different domain, different Q has stronger intensity. Now, in addition to that, there's also optical birefringence. So I will go into the results of the optical birefringence a bit in a bit more details, just because I feel like that the optical birefringence result is perhaps more free from the surface effect, since it has a more since the optical penetration depth is probing a bulk volume much more compared to the STM, and also require this amount of interpretation. So, at least to me, it seems to be a more straightforward and a more convincing evidence for rotational symmetry breaking. So here I'm showing you the optical birefringence results from the Yang Wu's group at UPenn, and then also the results from PKU in China. So what happens is that if let's say if you have a solids which has an isotropic refraction index, then when you shine a linearly polarized light into the solids, and then if your polarization is not aligned to the principal axis, then your polarization will rotate a little bit because of this anisotropy of refraction index. So Liang have measured this rotation of polarization, and I found out that this rotation angle onsets around the CW transition temperature. Similarly, the PKU also found something similar. So in this work, they have both of these groups have also discovered the optical rotation due to time reversal symmetry breaking. So this is the optical Curry effect. That is in addition to this optical birefringence. Now, the Capitoni group in Stanford, they are using a different technique that also measure optical Curry effect, and then their conclusion is that there is no optical Curry effect. However, through their measurements, they also concluded that there is a birefringence, which is shown in this figure, which I copied from their supplementary material. So you can see that even though this these three groups disagree on whether there is time reversal symmetry breaking or optical Curry effect, but they all agree that there is a optical birefringence. So to me, this seems to be quite a strong evidence that there is a rotational symmetry breaking at the CW transition temperature. Well, having said that, there's also a different view from different experimental groups. There's okay. So before I mention that, let me jump into this results, which is a even stronger claim than a rotational symmetry breaking, which is the evidence of nematicity. So I will explain more why this elastoresistivity measurements is an evidence for nematicity. But let me just say that in this paper, what they found is that they have done this elastoresistivity measurements, which is measuring the induced resistivity and anisotropy by a applied anisotropic stream. And then if you take the ratio of these two quantities, then you get an elastoresistivity coefficient. And then what they found is that this elastoresistivity coefficient is strongly enhanced below the CW transition temperature, which they argue that there is a nematic transition temperature below the CW transition. And yeah, so therefore they claim that there is a nematic transition below the CW transition. Okay, so far I have been talking about the evidence of rotational symmetry breaking, or even stronger claim nematicity. But there's also other experimental results that stated otherwise. For example, the Gershbaum groups from Rutgers University, what they've done is that they have done a very extensive Raman analysis and X-ray diffraction analysis. And then their conclusion is that the autoparameter of the CW is isotropic. It's in the A1G full symmetry mode. But they also found out that there could be a phase, a different kind of autoparameter that is energetically very nearby, so that and that autoparameter is breaking rotational symmetry, and that can be, and that small energy difference can actually be overcome, for example, by external stream. So therefore, their conclusion is that the true ground state of the system is isotropic, but all this previous anisotropic phenomenon people observed is due to a strain-induced phase transition, a strain-induced additional a new phase that is nematic or breaking rotational symmetry. Now, there's also some similar conclusion has been drawn by the Philip Morse group, which they have done some very interesting measurements using this focused ion beam technique of fabricating very well-shaped and then small micro-scale samples. So this is a work that is discussed in this preprint by Guo et al. So what they did is that they fabricated a structure which can make the sample almost well in a pristine strain-free condition. And then when they do that, they fabricate a hexagon and then put in contacts on the corner and then measuring resistivity along 3 principal directions. What they found is that if you're in a strain-free case, the resistivity along 3 directions are identical. Now, they can also glue the samples on a substrate, which will induce a lot of strain. And what they found is that once they glue the samples and then induce the strain, and then they see a substantial resistivity and anisotropy, and then based on their calculation up to 30%. They also see a resistivity and anisotropy induced by a C-axis magnetic field. Okay, so this is basically the third scenario, which is no rotational symmetry breaking, but some rotational symmetry breaking phases nearby that can be induced by strain. Okay, so now we have reviewed the situations in CVS. Let's talk a little bit about the nematicity and what is the difference between nematicity and rotational symmetry breaking, and how do we distinguish them. So okay, so the idea of nematicity was originated in the self-condensed matter physics, or in chemistry, where people study liquid crystals, and then in the most disordered phase, the most high temperature phase, you have the liquid phase where you have no orientation order and no periodicity. But as you cool down, you can enter into a phase that breaking the rotational symmetry without breaking translational symmetry. So therefore you have orientation order, but there's no periodicity, and this is called a nematic phase. And then if you cool further down, and you can enter into a phase where this is called a symplectic phase, which now you have periodicity, you have periodic order, and then you break translational symmetry while you're also breaking the rotational symmetry. So this idea has been borrowed by the condensed matter community in the strongly correlated phases, and then a very well-known example is the nematicity in the iron-based superconductor, where in the iron-based superconductor, you have a square tetragonal unit cell. And this unit cell, the ground state of the iron-based superconductor without any doping is a antiferromagnetic phase. So you have spin aligning ferromagnetic along one direction and then antiferromagnetic along the other direction. So therefore, in the ground state, you have a phase that break the rotational symmetry breaking because X and Y are different. And you also have the rotational symmetry breaking because you have double the unit cell by this antiferromagnetic modulation of spin. So this is the analogy of the symmetric phase. But what is very interesting in the iron-based superconductor is that if you raise the temperature, then there's actually an additional phase transition above this antiferromagnetic transition. And that phase transition actually corresponding to a short-range spin density or short-range antiferromagnetism, where you no longer have this long-range antiferromagnetic order, but the overall orientation of this short-range antiferromagnetic order is preserved. You can think of it as you have two kinds of spin fluctuation. One is corresponding to the spin fluctuation of a order that order antiferromagnetic along X direction, one going along the Y direction. But in this nematic phase, the fluctuation of one direction is stronger than the other. So that is precisely the analogy of the nematic phase in the liquid crystals. Okay, so some evidence for the nematic phase, for example, like you already see the rotational symmetry breaking. Here I'm showing you the you already see the evidence of rotational symmetry breaking above the neo transition temperature, the antiferromagnetic transition temperature. For example, here I'm showing you the lattice deformation, the structural distortion, where the A lattice constant and B lattice constant difference, and then you can see that the difference onset at the temperature above the neo temperature, the antiferromagnetic transition temperature. The other thing is that you can also probe the beer nematic susceptibility by the elastoresistivity measurement. So the idea is the following. The idea is that you have this electronic degree of freedom or the spin degree of freedom within the crystal lattice is driving this rotational symmetry breaking. Now the lattice environment is like a conjugate field of this nematic order. So very much like the magnetic field of the to the spins or to the magnetization. So if you can measure the response of the system when you're applying this conjugate field, and then measure how this response change as a function of temperature, then just like in the ferromagnetic case, where you can probe the ferromagnetic transition by a diverging magnetic susceptibility, here you can also probe the nematic transition by a diverging nematic susceptibility. And the response we're reading from the system is the anisotropic resistivity, rho XX minus rho YY, which should be linearly proportional to the anisotropic strain we're applying. So this linear coefficient is the nematic susceptibility. So here, this is a result of the iron-based superconductor, and you can see that this linear, the vertical axis is the resistivity and anisotropy. The horizontal axis is the anisotropic strain. And then you can see the slope changes very dramatically as a function of temperature. And then if you plot the slope, then you can see that it is increasing rapidly towards the nematic transition. And then in fact, you can fit this temperature dependence with a Curie-Weiss law, and then get a Weiss temperature that is a little bit 10 or 20 Kelvin below the actual transition temperature, which the reason I can explain if you're interested, but the important point is that there's a Curie-Weiss divergence, which is the signals is the smoking gun evidence of a nematic transition. Okay, so why is nematicity interesting? Now, I can give you a couple of reasons, but at least in the context of iron-based superconductor, it seems to be highly correlated with the superconductivity itself. So for example, here, this is a color map of the nematic susceptibility measurements I just showed you, the color corresponding to the strength of the nematic susceptibility. And you can see that the nematic susceptibility is strongest near the optimal doped transition. And here, this is a plot of the optimal, the superconducting TC versus the maximum of the elastoresistivity coefficient, which is nematic susceptibility. And you can see there's a strong correlation. So the nematic fluctuation seems to be strongly favoring superconducting pairing, which is an idea also being discussed and studied by the theoretical community. And then furthermore, this is a work done in a couple of years in my group at UW, which if you can actually use strain to control this nematic fluctuation, then you might be able to control the superconducting TC, since the TC and the nematic fluctuation is strongly correlated. So you can see that here, this is the resistance versus temperature curve of a iron-based superconductor, and then with a very large tensile strength or compressive strength, corresponding to red and blue curve, the TC of the system is being pushed towards zero temperature. So if we go back to the cesium vanadium 3 antimony 5 system and then look at their elastoresistivity measurement. So first of all, they do see a enhance of the elastoresistivity, which here this is called M11 minus M12, which is the E2G channel of the cesium vanadium 3 of the D6H group, and then corresponding to the nematic channel. Now they have fitted with this 5 data point with the Curie-Weiss curve, and then get a Weiss temperature of around 22 Kelvin, and then so therefore their conclusion is that there is a nematic transition well below TCEW that giving rise to this Curie-Weiss like susceptibility. So I'll leave it to you to decide whether this fitting is convincing. Nevertheless, I think this Korean group that Peng-Chun mentioned at the beginning, they follow up on this work and then continue the measurements, and then what they found is that if you keep doing the same measurements and doing the same fitting, they found a enhanced nematic susceptibility in this titanium substituted cesium vanadium 3 antimony 5, and then the enhancements of the nematic susceptibility happen to coincide with the first superconducting dome, so suggesting that maybe a similar scenario is happening here, similar to the iron-based superconductor, where nematic fluctuation is somehow responsible or helping the superconducting pairing within the system. So you may argue that, okay, what's why are we interested in this nematic phase in the cesium compound, since the iron-based superconductor? No, it's the same story, iron-based superconductor. What's new here? So what is new here is that if all this is true, then we're seeing a nematic transition in a hexagonal crystals. So in hexagonal crystal, this nematicity is different from the tetragonal crystal, which is iron-based superconductor. So the iron-based superconductor, as I show you, the nematicity have only two options. It can only go to X direction or Y direction. So in some sense, it is a Ising variable. It's an Ising nematicity, +1 corresponding to X, -1 corresponding to Y direction. Now here in hexagonal system, you have three options. You can go to 0 degree, 120 degrees, or 240 degrees. And in this case, then the phase transition becomes a three-state path model, or three-phase path transition, which is already different from the Ising transition. And their strain response is also fundamentally different. So in the case of Ising nematicity, if you apply strain, it only smear out the transition, just like what I show you for the superconductivity, it suppress the fluctuations, and then therefore turn the transition into a crossover. Now, in a three-state path system, if you apply strain, then depends on whether you're applying for tensile strain or compressive strain, you'll see a different result. So this is summarized by a theory paper by Rafael Fernandez a couple of years ago, which was discussed in the context of the twisted bilayer graphene, but it applies to any three-state path nematicity in this hexagonal or triangular system. So in the so this depends on the coupling constant, but let's say in the tensile strain, you will expect a nematic flop transition where which is an icing transition where you're going from let's say going from 0 degree, and then this nematic director will have to suddenly choose between plus 30 degree and minus 30 degree. Or if you do a compressive strain, then it becomes a nematic crossover where the nematic direction is unchanged, but the odor parameter enhance suddenly when you're going across this crossover transition. So you already see a very rich and different behavior as a function of strain for the three-state path nematicity. Furthermore, if you think about the quantum phase transition, that is, if you find a way to tune this three-state nematic transition to 0, you are also seeing a very different behavior for post-nematic quantum phase transition and isinematic quantum phase transition. So isinematic quantum phase transition is a second-order phase transition, which will end in a second-order nematic quantum critical point, and then this is basically what the scenario in the iron-based superconductor, which you already see some very interesting interplay between the Fermi liquids and this nematic quantum critical transition. Things like non-Fermi liquid behavior, linearity resistivity, or this superconductivity, high temperature superconductivity, and then the TC sensitivity to strain. In the post-nematic transition, which is summarized by another more recent paper by Rafael and others, you will expect a first-order quantum phase transition for a post-nematic transition. However, if you apply strain, again, depends on the direction of the strain, depends on the sign of the strain, tensile or compressive strain, you'll end up in a quantum critical endpoints or a quantum tricritical point. So therefore, you can use strain to approach to second-order quantum critical point, which could potentially also have interesting results on superconductivity and the Fermi liquid behavior. Now, this is totally unexplored. And at this point, there's only a few candidates for three-state path nematicity, such as the iron intercalated niobium sulfide. So this was studied by Joe Ornstein group and James and Elitis group in Berkeley. And there's also some of the recent study by us with Xiaodong and also Liang Wu's group on this transition metal phosphorus selenite. So they all show some behavior that is consistent with the three-state path nematicity. Nevertheless, all this compound is not. But first of all, they are magnetic materials. So the vanadium compound is a charge order compound. So just have a different kind of flavor of nematicity is already quite interesting. Secondly, these two compounds, it's unclear how you can tune these phase transitions, this three-state path transition in these two systems to 0 temperature to induce a quantum phase transition. Whereas in this cesium vanadium 3, you already have a quantum phase transition, you already have a superconducting dome. So if there's really a three-state path nematicity in this system, that would be very interesting to study. Okay, so now telling you how interesting this will be, I'll have to follow with a section of telling you the bad news that there's actually no nematicity in this system as shown in our measurements in the cesium vanadium 325 compound. Okay, so so let's review what we know so far, all this experimental evidence in the cesium vanadium 3. So there's a rapid increase of this EG elastoresistivity coefficient, which corresponding to a nematic transition at a temperature much below TCW. Now, this is already very strange because if you recall what we observed in the iron-based superconductor, the nematic transition is always above the CW transition because you break rotational symmetry first, and then the CW breaks rotational symmetry, and then the translational symmetry. So the only logical conclusion you can draw from if you believe this divergent nematic susceptibility is that the first possibility is that the rotational symmetry is not broken at the TCW. So therefore, you are entering into isotropic CW states. And then at the T star, there's a nematic transition. So therefore, you have a divergent nematic susceptibility below the CW transition. Now, this is inconsistent with a lot of the experimental work that have shown that the rotational symmetry is already broken at the CW. So therefore, there's another explanation, which I think is the explanation adopted by these authors, which is that the rotational symmetry is only weakly broken at the CW transition. For example, if you have a stacking between, you have a stacking of this start of David and trihexagonal pattern in this compound, which from one layer to the other, if there's a phase shift. So therefore, even though your CW within each layer is isotropic, but the bulk of the sample, because of the stacking phase shift inducing a rotational symmetry breaking, the unit cell become orthorhombic because of this stacking pattern. Now, in this case, this could be considered as a weak rotational symmetry breaking because within the plane, you still have a more or less isotropic. And then it's really the interplane coupling, this phase shift, that give rise to a direction. And so it could be that you have this weak rotational symmetry breaking at higher temperature, but at lower temperature, you have a stronger rotational symmetry breaking within the plane by forming some sort of anisotropic CW within the plane. So this is the second scenario. And then the third scenario is that there's something wrong with the measurements. So let's look at their measurement configurations. So if you look at their measurements, schematics, what they have is that you have a piezo stacks, which is responsible for generating an isotropic stream. And then you glue the crystal on the piezo stack. But they have two samples, two bar-like samples, two matchstick-like samples that gluing along the orthogonal directions. The reason for doing that is because you need to do symmetry decompositions in elastoresistivity measurements. Let's say if you glue a single samples and then measure along one directions and then measuring, let's call this direction X, and then you're measuring the Rxx of a sample as a function of strain, which is inducing by the applying voltage to the piezo stack. So when you apply voltage to the piezo stack will expand along the pulling direction, this direction, and then contracting along the transverse direction. But the degree of pulling and the degree of the contracting along the two orthogonal directions is not the same. So therefore, you're simultaneously applying a strain that is that can be described by a pure epsilon xx plus epsilon yy, and a pure epsilon xx minus epsilon yy, which is the anisotropic component. So this is an isotropic component, this is an anisotropic component. So you're applying a superposition of these two. And then in the language of group theory for the D6H groups, so one is A2G, the other is A1G. Now, when you measure in the Rxx is can also be decomposed into two components. It's the rho xx minus rho yy and then rho xx plus rho yy. And this two channel each are linearly proportional to the anisotropic strain and isotropic strain. So therefore, to isolate the anisotropic part and the isotropic part, you have to also measure RYY. And then therefore, this is why you in this technique, this is called differential elastoresistivity technique. You glue a sample orthogonal to the original direction, measuring the orthogonal direction. And then you take the difference, you get the anisotropic component. You take the sum, you get the isotropic component. Now, this will work if each sample is experiencing exactly the same amount of the anisotropic strain isotropic strain. So meaning that the E2G and A1G ratio within each sample is exactly the same. If they're exactly the same, then when you take these difference and sum, you can exactly cancel and then get the pure anisotropic part and the pure isotropic part. Now, in reality, this is never true especially for this kind of bar-like samples. The reason is that when you glue the samples on the piezo stack, it's only the bottom part is adhered to the surface of the piezo stack. And then when you deform the piezo stack, the strain will relax towards as you go through the thickness of the samples. Now, the degree of relaxation depends on the aspect ratio of the lateral direction, the lateral dimensions and the thickness. So if you have a very large lateral dimension, for example, like in this case, and a very thin samples, very short thickness, then there's negligible strain relaxation. And then in contrast, if your thickness and then your lateral dimension is comparable, then you're experiencing a very strong strain relaxation. So now if you look at this two sample, then you can immediately see that you expect almost no strain relaxation for the x directional strain for this sample, but a lot of strain relaxation along the y direction. And then for this, you will have the opposite. You will have almost no strain relaxation along the y direction, full strain transmission along y direction, and then a lot of strain relaxation along the x direction. So therefore, for this sample, it is almost experiencing epsilon xx. The other sample is almost experiencing epsilon yy. And then therefore, their A1G and E2G component the ratio are completely different. So when you take the difference, then what you will get is a mixture of the isotropic and A1G, isotropic and isotropic A1G response and isotropic E2G response. Okay, so what's the solution? So the solution is to get a square samples where and then a large samples where you put contacts on the four corners, and then therefore you can simultaneously measuring rho XX and rho YY. And then and you also get the same kind of strain relaxations or strain transmission condition for both X and Y direction. And then you can even put a strain gauge on top of the sample to measure the strain transmission. And this is called the Montgomery technique. So we have done three elastoresistivity techniques. So in addition to this differential technique, we did Montgomery techniques, and this is called a transverse technique, which is similar to Montgomery technique, which you're also measuring in single samples. So therefore, you also don't suffer from this strain transmission problem. So what we found is that this single sample technique yields a consistent and similar results, which is you have a stronger A1G response here, and then a very weak E2G anisotropic response. And whereas if you're using a differential technique, then you're getting strong and then similar temperature dependence in the E2G response to the A1G response. And this is because this is really coming from the contaminations or leakage from the A1G channel. Okay, so so let's look at the measurements let's look at the results from the Montgomery technique, where you see a very strong A1G response with a peak at the TC level transition temperature, and then followed by a very strong increase at low temperature. And then in the anisotropic E2G nematic response, you see it almost temperature independent. So this is in sharp contrast with the iron-based superconductor results I just showed you, where the blue is the B2G response, which is the anisotropic nematic response. You see there's a very strong response, go all the way up to 115. And then the A1G is isotropic. So this is completely opposite in the cesium vanadium 3 antimony 5. And this peak of elastoresistivity in A1G can be explained by the is actually proportional. It looks like the d rho dt, which is also look like the heat capacity anomaly. So this can be understood in terms of a generalized Fischer-Langer theorem, which is when your A1G is linearly shifting the transition temperature. So locally, the effect of applying strain is like changing the temperature. So therefore, the rho d strain is just like the rho dt. So therefore, you have a peak-like structure near the phase transition. So here I'm superimpose the rho dt with the elastoresistivity, and you can see this two feature matches very well. Now, if you remove this feature by using the rho dt as background, what you're left is something like this, something that is peak around 20 Kelvin. And then we have also measured the anomalous Hall effect on these samples, and then we found out that the anomalous Hall effect somehow have a very similar temperature dependence as this A1G elastoresistivity. So, and then this same temperature dependence is also similar to the non-reciprocal transport effect, the magneto-Cairo effect discovered by Philip Moore. Okay. Okay, so we have also done another measurement, which is called the elastocaloric measurement, elastocaloric effect, which is you're applying a small oscillating strain, and then you see how the temperature change, temperature oscillation induced by this small oscillation. So you're basically measuring the change of temperature induced by strain in an adiabatic condition. And this is a way to probing the entropy landscape of your system. So there's two elastocaloric effect that is relevant here to in our context. So let's again use iron-based superconductor as an example. If you're applying a strain that is not conjugate to the nematicity, for example, just applying a orthogonal channel A1G strain, or in the tetragonal system, you can apply B1G strain since the nematicity is B2G. Then what you found is that this strain won't smear out the transition, but it will shift the transition temperature. So kind of similar to the A1G elastoresistivity, what we're seeing, you're also going to see a change of the temperature due to a change of the transition temperature. And you'll see a anomaly that looks like a heat capacity anomaly. And that is primarily due to the fact that you're shifting the temperature. So therefore, the system as you're getting close to the critical temperature, the entropy changes dramatically as you're shifting in and out of phase transition. So therefore, you're seeing a heat capacity anomaly near the phase transition, and that anomaly will be proportional to the TD strain. Okay, so this is the case in an iron-based superconductor applying a orthogonal strain. However, if you're applying a strain that is conjugate to the nematicity, then because you are going to induce the nematic autoparameter above the phase transition, you're going to change the free energy. So you will see a divergent-like response here. And then that response will proportional to strain, because the more you're applying strain, and the more the free energy you change. And then you can see that this different color curve corresponding to different strain. And then with a larger strain, you can see that there's a stronger and stronger diverging response. And that diverging response is proportional to chi dt. So, okay, so now we can applying this technique to the cesium vanadium for antimonate 5. And in this case, since if you actually stretch the samples, you're simultaneously inducing an A1G strain that will shift the transition temperature, but also an isotropic strain that, if there's any nematicity, will couple to that nematicity and then give rise to this diverging response. So here is the results. What we see is that there's only a heat capacity anomaly near the critical temperature. There's a very smooth and curve, and then nothing significant below the transition temperatures. Similarly, above the transition temperature, we also see nothing, just a flat curve, indicating that there's no sign of a nematic transition. And then this heat capacity anomaly shift as a function of strain. And then, so this is precisely matching the expectation of the A1G strain that is shifting linearly with the transition temperature is shifting linearly with the A1G strain. And if you recall, early on, we have discussed that there's some some studies suggested that there's a nearby states that could be induced by strain. Now, if that is the case, then we should expect a strain-induced phase transition, which should also show up in this elastocaloric effect. Nevertheless, we see no sign of this. We only see this shifting of the critical temperature. So whatever that strain-induced phase transition, it is not within this. At least it is not within this strain range we are applying, which is quite high now compared to the kind of strain you're going to expect it from, for example, gluing on the substrates or things like that. Okay, so this shift of the transition temperature is consistent with a very nice work done previously by Nini's group in UCLA, which they have carefully compared the strain-induced transition temperature with the pressure-induced change of the transition temperature, and then plotting all kinds of parameters, and then concluding that the dominant control parameter for this transition temperature is the c-axis, the change of c-axis. So our work is consistent with theirs. Okay, so right after we submitting our archive paper, there's also two other preprints. So there's this paper by the Matsuda groups and Shibachi groups where they have also done elastoresistivity measurements, and then their elastoresistivity results is consistent with ours, dominating A1G response, a peak at the transition temperature, and then a strong temperature dependence in A1G, but almost temperature independent in the E2G nematic channel. But very curiously, they also found a additional phase transition above the CEW transition from the torque measurements. And we have also done some measurements with the so basically they are suggesting that there's a field-induced or there's an odd parity nematic phase that will couple to the magnetic field, a transition above the CEW transition. So we have also done elastocaloric measurements under different magnetic field, but we're basically seeing no response at all above the CEW transition. So yeah, so we didn't see that transition. Now there's another paper by the German groups, which they have also done the elastoresistivity measurements and the thermal expansion. So again, their elastoresistivity is also consistent with ours, which is a strong A1G response. They have slightly different analysis method, and then which they don't see the peak below the A1G, below the CEW transition temperature in the A1G channel. But the overall behavior is very similar. And then from the thermal expansion, they also didn't see additional phase transition above the CEW, and then they see a dominant c-axis response, similar to the analysis of pressure and strain dependence of transition temperature. Okay, I think that's all I want to talk about. So I'll just leave the summary here, where we have seen no evidence of nematic transition in this compound, but a very strong A1G response in cesium vanadium 3-antimonide. Thank you for your attention.
Yeah, thank you, Jiun-Haw. Yeah, extremely comprehensive and very nice, result. So one of the questions that people might want to ask is that when you do these elastoresistance result, you have to sort of glue your sample on the piezo electric. I mean, how well, I mean, how important the alignment of the crystal axis with respect to the piezoelectric in terms of this type of measurement that you do.
So for iron-based superconductor, it is more important because in iron-based superconductor, it's only if you're aligning along the iron arsenide direction, it's B1G. If you're aligning with the iron bonding direction, it's B2G. But for the hexagonal symmetry point group, it actually doesn't matter because the anisotropic is a two-dimensional irreducible representation. That means that both the shear strain epsilon xy and epsilon xx minus epsilon yy, they are the two components of this two-dimensional array. So that means that you can point to any directions of the crystal with respect to your crystal axis in plane. You'll get the same linear response. So the nonlinear response will be different, but the linear response will be exactly the same, no matter which direction you're pointing. If there's an anisotropic response there.
So how do you then understand the the Korean group's result, where he look at the titanium dope sample and see this sort of a so-called A1G regime reducing with increasing titanium doping?
So you mean this result?
Yeah. You have a figure showing, yeah.
Right. So my understanding that I think these are still A1G contamination, and
okay.
And well, I mean, you can see the diagram of their measurements, which is still using these two samples, which is I know in their paper, no, so they have also for their paper they also have published a review. I think one of the reviewer asked them to do this Montgomery technique, and then they have done, according to them, they have done Montgomery measurements on one doping, and then they said that the Montgomery results and the differential results yields the same results, which strictly speaking, we have to measure exactly the same sample with the Montgomery method to see if this is really true. But I think it's very unlikely that you suddenly have a simultaneous response in one doping, but in the parent you have one dominating the other. Yeah.
So let me ask you the other question then. Are you suggesting then this temporal symmetry breaking and anomalous Hall effect that people claim to have seen earlier is potentially due to the fact that it's being glued on some sort of substrate induced by strain?
Not really. Well, so we have done a measurements which is straining a sample and then simultaneously measuring the anomalous effect. We see no change of the anomalous effect as a function of strain. So whatever that response is, that seems to be very insensitive to strain. So yeah.
Okay, well that's actually, yeah, I find your work is very enlightening. Yeah. Any other question from the audience?
Hey, Jiun-Haw, very nice talk. It's Ross here.
Hi, Ross.
A quick question just about the actually, if you can you show your last concluding slide?
Yeah.
Because I think you had the units on there for the. So I make you jump all the way to the end.
Yeah.
Yeah, that one. So the units on the vertical axis on your top graph, Kelvin, is that taking into account strain as a percentage or absolute strain when you divide by dt dE? So how big is that temperature shift when you actually measure it for those strains? Because I was expecting to see a millikelvin number there, but maybe.
Right. So I think it will be. I think it's the absolute value. So therefore.
Okay.
Right.
So in reality, you're measuring small temperature changes, millikelvin.
Exactly. Yeah.
Dividing by not 0.1%. You're dividing by, okay.
Exactly. Yeah.
Just checking, because somewhere through this, I went from seeing what looked like millikelvin changes to Kelvin, and then was like, it must just be how strain is treated. But
right.
Yeah. Okay. Thank you. Nice talk.
Thanks.
Yeah. No. Extremely nice talk. Yeah. Any other questions? So what are you basically saying? I mean, Jiun-Haw, you're basically saying that there's no phase transition period based on your last measurement below CDW, except for superconductivity, right?
Right. So I mean, from the elastocaloric, there's no sign of phase transition. Well, okay. Or if there's a phase transition, so here's what you expect from the elastocaloric effect, right? So you'll see a response if there's a transition temperature that would change by A1G strain, which in principle it should change no matter what, and because you're slightly changing the lattice, and then therefore the transition temperature will change. So it's just a matter of how large it is, and and then the fact that we're seeing extremely smooth curve below the CW transition meaning that that transition is probably, if there's really such a transition, then it's coupling very weakly to the lattice, so that there's almost no change of the transition temperature due to the lattice, and also the heat capacity anomaly is extremely small, so this would be below our resolution limit.
Yeah, that's actually extremely convincing to me. Yeah. Okay, I mean, if there's no other talks, yeah. Thank you so much, Jiun-Haw. Yeah.
Thank you, Bong Chen.
Yeah. Bye.
Bye.